March 14th, 1944. Republic Aviation Field, Farmingdale, New York. The wind swept across Long Island with a late winter bite, sharp enough to make even seasoned airmen hunch inside their coats, their breaths puffing in small clouds that vanished almost as quickly as they formed. A thin haze lingered over the tarmac, stubbornly clinging to the cold asphalt, only to be disrupted by the steady growl of radial engines warming on the apron. Mechanics scurried between hangars, checking oil levels, tightening bolts, and running last-minute diagnostics, their movements precise yet hurried, as if the machines themselves demanded respect before taking to the sky. Alexander Kartveli, chief designer at Republic Aviation, stood apart from the bustle, his gloved hands clasped firmly behind his back, his posture both rigid and contemplative. His eyes followed the P-47 Thunderbolt as it climbed steadily into the grey morning, the massive Pratt & Whitney R2800 double Wasp engine, pulling the 8-ton fighter with deceptive ease. He could see the sunlight glinting off its metallic fuselage, highlighting the sleek lines and reinforced armour that had been painstakingly engineered to protect the pilot and withstand the rigours of combat. Kartveli's mind, however, was far from the beauty of the aircraft in flight. It raced through calculations, aerodynamic refinements, and the endless series of modifications that had led to this moment. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Nearby, ground crews signalled and checked gauges, their shouts muffled by the roar of engines and the whipping wind. Each Thunderbolt that lifted off represented countless hours of labour, not only from engineers like Kartveli, but from thousands of factory hands who had poured sweat and skill into the production lines. He knew every rivet, every control, surface, every panel of armour had been designed with precision, tested under impossible conditions, and iterated again and again. The thought was both humbling and exhilarating. This machine was not just a fighter, it was a promise of technological superiority, a tool that could tip the scales in the war that raged across the globe. As the Thunderbolt arced gracefully against the overcast sky, Kartveli allowed himself a rare moment of satisfaction. The P-47 was fast, durable, and lethal, a combination that had earned it a reputation among both pilots and adversaries. Yet he also knew the stakes. Each sortie flown by these aircraft carried men into the very heart of conflict. Lives hung in delicate balance, dependent on engines, armour, and the ingenuity of designers who would never leave the ground. Kartveli's chest swelled with pride, tempered by a quiet solemnity. Engineering had given him wings to shape the war, but with those wings came immense responsibility. The cold wind cut, deeper as he turned back toward the hangar, the distant roar of the climbing Thunderbolt fading into the morning. The day ahead would be long, more tests, more calculations, more refinements, but in that fleeting moment, standing on the frost-laden tarmac, Kartveli allowed himself to feel the thrill of creation. Here, in the heart of Long Island, he had helped craft a machine that could soar above the chaos of war, a testament to human ingenuity and resolve, forged in steel and powered by the roar of 1,000 ambitions. The 8-ton fighter looked almost graceful from the ground, its massive Pratt & Whitney R2800 double Wasp engine dragging its big frame upward with deceptive ease. The Thunderbolt did not look like a plane that should be able to fight, let alone dominate. It looked like something that should plough fields or haul freight. But Kartveli knew better. The Thunderbolt was a creature of its own kind, a machine built not around elegance, but power. Built to dive, strike, and survive. Beside him, a young Army Air Forces captain shifted uneasily. Robert S. Johnson, just 24, wore the uneasy posture of a man who had only recently stepped out of a cockpit and into civilian clothes. He was not comfortable on the ground. He had 27 confirmed kills, but his real value today was not his victories, it was his experience. He was one of the few pilots who had truly pushed a Thunderbolt to its limits and survived to talk about what happened when he did. 3 days earlier, in a small room at Wright Field, Johnson had described a dive over France so steep, so fast, and so uncontrolled that even he had been afraid. His Thunderbolt had hit speeds as high as 550 miles per hour, far above what the engineers claimed was safe. The propeller had stayed course, the engine had held steady, the controls had stiffened, but the aircraft had remained stable. No flutter, no failure, no catastrophic disintegration. He should have lost control, but he didn't. Instead, he outran German fighters that had no hope of following. Kartveli had listened, silent, unmoving, except for the slow tightening of his jaw. The performance Johnson described should have been impossible or at least dangerous. The physics said so. The engineering reports said so. But the battlefield did not care about reports. It cared about results. Now, standing on the tarmac, Kartveli was seeing those results for himself. The prototype Thunderbolt above them executed a shallow turn, then pitched down gently at first, then more aggressively. Kartveli watched closely as the nose dipped lower, the wings slicing downward through the cold air. Johnson watched too, his breath held without meaning to. The distinctive whistle of compressing air, sharp, piercing, mechanical, grew louder. Then, instead of buffeting, instead of vibration, instead of instability, the P-47 held steady, as though cutting through glass. It was diving, hard, fast, and stable. Kartveli frowned not in disapproval, but in realization. He had not designed this capability. Not intentionally. He had designed for power, reliability, survivability, yes, but not this. Not 500-mile-per-hour dives. Not control surfaces holding firm in deep transonic descents, and certainly not propellers that stayed coarse and efficient at speeds that should have torn the plane apart. "Explain it again," Kartveli said quietly, not taking his eyes off the diving plane. Johnson exhaled slowly, his gaze following the Thunderbolt. "Sir, it doesn't nose over like you'd expect. It just keeps going. No flutter, no pitch change. You keep the throttle open and she accelerates all the way down. You can catch anything, or outrun anything." Kartveli nodded, very slowly. He knew the truth now. The Thunderbolt was more than what he had designed. It had become something greater, shaped not only by wind tunnels and drafting tables, but by pilots, by real combat, real pressure, and real innovation that sometimes happened thousands of feet in the air, far from any engineer's reach. An airplane designed for strength had accidentally become a master of speed. The Thunderbolt leveled out just above the horizon, its engine roaring as it passed the airfield in a screaming low pass before climbing again, graceful as a bird that did not know it was heavy. Kartveli finally spoke, almost to himself. "It seems," he said quietly, "that our airplane has discovered something we did not." Johnson smiled. One pilot's smile to an engineer's revelation. And in that moment, both men understood. Sometimes the sky teaches what the ground never imagined. The P-47 could not dive. Or rather, it could dive, but not the way combat demanded. When Thunderbolt pilots pushed their aircraft into steep dives to escape German fighters or pursue fleeing enemy aircraft, something terrifying happened at speeds above 450 miles per hour. The propeller, that 11-foot disc of Curtiss Electric spinning metal at the Thunderbolt's nose, began to act not as a propeller, but as a brake. In high-speed dives, the massive four-bladed propeller would automatically shift to fine pitch, increasing drag so dramatically that pilots felt as though they had deployed a parachute. Aircraft that should have been accelerating to 550 miles per hour or more were limited to 450, maybe 470 in optimal conditions. German Fw-190s and Messerschmitt 109s, lighter and more aerodynamic, could dive away from pursuing Thunderbolts with ease. Worse, when Thunderbolt pilots tried to manually override the propeller pitch control to coarsen the blade angle and reduce drag, the propeller sometimes refused to respond. Or it would shift to coarse pitch and then slam back to fine pitch without warning, creating massive control problems at the worst possible moment. Several pilots had nearly been killed when their aircraft became uncontrollable during high-speed dives. Johnson had explained all of this to Republic's engineers in language that was technically precise but emotionally raw. He had watched German fighters escape. He had felt his Thunderbolt shudder and slow when it should have been gaining speed. He had struggled with propeller controls that seemed to have minds of their own. And he had come home with a simple question that nobody at Republic or Curtiss Electric seemed able to answer. Why couldn't they fix it? The answer standing on the tarmac that morning was not an engineer from Republic or Curtiss. His name was Harold Neumann, and he was a civilian propeller specialist who had spent the last 3 months making himself deeply unpopular with both companies by insisting their solution to the P-47's diving problem was fundamentally wrong. Neumann was not an aeronautical engineer. His background was in mechanical engineering and manufacturing. He had worked for Hamilton Standard propellers before the war, and he understood propeller dynamics in ways that were more intuitive than theoretical. When he looked at the massive Curtiss Electric propeller on the Thunderbolt, he saw something everyone else had missed. The propeller blades were bent wrong. Not damaged wrong, but designed wrong. And fixing that design error would require doing something that seemed completely counterintuitive. They needed to bend the propeller tips backward. Kartveli had listened to Neumann's proposal 3 weeks earlier with the kind of patient skepticism engineers reserve for ideas that sound too simple to work. Propeller blade design was not simple. The blades were not flat surfaces but carefully sculpted airfoils that changed pitch along their length. The tips travelled at supersonic speeds even at normal engine RPM. The forces involved were enormous. The Curtiss Electric propeller on the P-47 was a masterpiece of engineering, a hydromatic, constant-speed propeller that automatically adjusted blade pitch to maintain optimal engine speed under varying flight conditions. Its governors and pitch change mechanisms represented thousands of hours of development. And Neumann was suggesting that the fundamental blade geometry was wrong. The problem, Neumann explained, was compressibility. At high speeds, the propeller tips were encountering air that behaved differently than at low speeds. As the aircraft dove and airspeed increased, the relative wind striking the propeller blades created aerodynamic forces that the automatic pitch control system interpreted as a need to shift to finer pitch. The system was doing exactly what it was designed to do, but the design assumptions were wrong for high-speed flight. By bending the propeller tips backward, changing their angle of attack relative to the airflow, Neumann believed they could alter the aerodynamic forces acting on the blades during high-speed dives. The modified blades would naturally want to maintain coarser pitch, fighting against the automatic system's tendency to shift to fine pitch. The result would be a propeller that remained in efficient high-speed configuration during dives, dramatically reducing drag. Republic's engineers had done the calculations. The math was ambiguous. Some formulas suggested Neumann might be right. Others indicated the modification would make handling worse. Wind tunnel testing would take months. The only way to know for certain was to build a modified propeller and test it in actual flight, including high-speed dives that pushed the aircraft to its limits. Kartveli had authorized the test, but he was not confident. Too many variables, too many unknowns, too many ways for this to go catastrophically wrong. If a modified propeller failed during a high-speed dive, the resulting crash would kill the test pilot and probably set the program back 6 months. But Johnson's testimony had made clear that the current situation was also killing pilots, just more slowly and in combat, where the deaths were attributed to enemy action rather than design defects. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The test aircraft that morning carried propeller number 473A, a standard Curtiss Electric unit that had been carefully modified by Neumann himself over the previous week. He had heated the blade tips and bent them backward exactly 7 degrees from their original angle. The modification looked crude, almost amateurish. The bent tips disrupted the propeller's elegant lines. Engineers from Curtiss Electric had visited 3 days earlier, looked at the modified propeller, and walked away shaking their heads. Major James Goodson would fly the test. Goodson was another ace, a veteran of combat over Europe with 15 confirmed victories. He had experienced the diving problem firsthand and had volunteered to test the modification. As Goodson walked toward the aircraft that morning, Kartveli noticed the pilot was not wearing his usual confident expression. Nobody knew what would happen when Goodson pushed that Thunderbolt into a vertical dive at 25,000 feet. The test protocol was straightforward. Goodson would climb to 25,000 feet, establish level flight, then push the Thunderbolt into the steepest dive the aircraft could achieve. He would note propeller behavior, control response, and maximum speed attained. If anything felt wrong, he would immediately pull out and return to base. If the propeller failed structurally, there was nothing the protocol could do to help him. Kartveli watched the Thunderbolt disappear into the overcast. The waiting began. On the ground, there was nothing to do but monitor the radio and watch the sky. Neumann stood apart from the Republic engineers, knowing his presence was tolerated rather than welcomed. He had pushed this test forward, against institutional resistance, and if it failed, he would be blamed comprehensively. 27 minutes after takeoff, Goodson's voice came through the radio. Beginning dive run. The transmission was clipped, professional, revealing nothing about what Goodson was feeling as he nosed the Thunderbolt toward the Earth 5 miles below. What happened next would be described by Goodson in a debriefing 2 hours later, but the men on the ground could only wait and listen to sporadic radio calls that marked the dive's progress. 420 miles per hour, propeller steady. 450 miles per hour, controls responsive. There was a pause that seemed to last forever. Then Goodson's voice again, higher pitched, excited. 480 miles per hour. No prop shift. 500. 520. Controls still good. 540. Kartveli felt something unclench in his chest. The Thunderbolt was diving faster than any P-47 had dived before. And Goodson was reporting that the propeller was remaining in course pitch, that the controls were responsive, that the aircraft was behaving exactly as Neumann had predicted. 550 miles per hour. Pulling out. The Thunderbolt emerged from the overcast like a thunderbolt indeed. Goodson pulling 6 Gs to level out at 8,000 feet. He circled the field once, his wing over a victory roll in all but name, then brought the aircraft in for a landing that was smoother than the circumstances warranted. When Goodson climbed out of the cockpit, his face was flushed with adrenaline and something close to joy. "It works," he said simply. "The damn thing works. I hit 550 miles per hour, and she was still accelerating. Propeller stayed course the whole dive, pulled out smooth as silk. We can outdive anything the Germans have." The engineering team swarmed the aircraft, inspecting the modified propeller for damage, checking control systems for anomalies, downloading data from the limited instrumentation available. What they found confirmed Goodson's report. The propeller had remained in course pitch throughout the dive. Blade stress was within acceptable limits. Control responses were normal. Neumann's crude modification had transformed the P-47's diving characteristics. What nobody on the ground that morning fully grasped was how completely this would change air combat over Europe. The tactical implications were enormous. The P-47 Thunderbolt was already the heaviest single-engine fighter in American service, weighing over 13,000 pounds fully loaded. That weight, combined with the powerful R-2800 engine, producing 2,000 horsepower, gave the Thunderbolt tremendous energy retention and speed in level flight. But the aircraft's greatest tactical advantage had always been theoretical rather than practical. The Thunderbolt could, in theory, dive at speeds no German fighter could match. Its robust structure could handle stresses that would tear apart lighter aircraft. Its engine could produce full power at high speeds where other engines would fail. But the propeller problem had negated all of these advantages. German pilots had learned that they could escape from Thunderbolts by diving. The Fw-190, in particular, could roll into a steep dive and accelerate away from pursuing P-47 seconds because the American aircraft's propeller would prevent it from following. This escape tactic had saved countless German pilots and frustrated American fighter pilots who watched their prey escape despite flying superior aircraft. Neumann's modification reversed the tactical equation completely. A Thunderbolt with the modified propeller could now dive at speeds approaching 550 miles per hour, perhaps even higher under optimal conditions. The Focke-Wulf 190 began experiencing structural problems above 480 miles per hour. Its wings would twist, its control surfaces would lock up, and in extreme cases, the aircraft would begin to disintegrate. The Messerschmitt 109 had similar limitations, though its lighter structure made it even more vulnerable to high-speed compression problems. German fighters that dove away from Thunderbolts would now find American fighters not only following but accelerating past them, closing the range with terrible inevitability. And if German pilots tried to pull out of dives at speeds above 480 miles per hour, their aircraft would break apart from the G-forces, while the massively built Thunderbolt would pull out safely. The modification created a combat scenario where the Thunderbolt's natural advantages became overwhelming. American pilots could dictate the terms of engagement, attacking from high altitude, diving at speeds no German fighter could match, and either destroying the enemy in the dive or following them to lower altitude where the Thunderbolt's weight gave it speed advantages. German fighters that tried to escape by diving were choosing between being caught by faster American aircraft or pulling out so hard their planes broke apart. But translating a successful test flight into combat reality required navigating military procurement bureaucracy and overcoming resistance from Curtiss Electric, the propeller manufacturer. The modification worked, but it was not Curtiss's modification. It had come from an outsider, a civilian specialist who had made Curtiss engineers look incompetent. The company's pride was wounded, and wounded institutional pride is dangerous. Curtiss Electric insisted on conducting their own tests. They argued that Neumann's modification was crude and might cause long-term reliability problems. They suggested alternative solutions that would require 6 months of development and testing. They raised concerns about propeller balance, blade stress, and maintenance complications. Every concern was technically legitimate, but the cumulative effect was to delay implementation of a modification that could save American pilots' lives immediately. Kartveli and Republic Aviation found themselves in an uncomfortable position. They had proven the modification worked. Combat pilots were demanding it. But Curtiss Electric controlled propeller production, and without Curtiss's cooperation, the modified propellers could not be manufactured in the quantities needed to equip combat squadrons. The solution came from an unexpected direction. Colonel Hub Zemke commanded the 56th Fighter Group, one of the first P-47 units deployed to Europe. Zemke was not just a commander but a pilot who understood both tactics and technology. When he heard about Neumann's modification through informal channels, he immediately grasped its importance. Zemke had watched too many German fighters escape by diving. He had lost pilots who pushed their Thunderbolts too hard, trying to follow enemy aircraft into high-speed dives. In late April 1944, Zemke flew back to the United States for a brief consultation period. He visited Republic Aviation, test flew an aircraft with the modified propeller, and then went directly to 8th Air Force headquarters with a simple message: either get the modified propellers into combat squadrons immediately, or explain to the bomber crews why their fighter escort could not catch German fighters that attacked and then dove away. The institutional logjam broke. By mid-May, Republic Aviation received authorization to modify propellers in England using local facilities. Curtiss Electric, facing the prospect of being bypassed entirely, suddenly discovered that the modification could be standardized and manufactured to proper specifications. By June 1944, the first combat squadrons were receiving Thunderbolts with modified propellers. The pilots noticed the difference immediately. Captain Walker Bud Mahurin, who would finish the war with over 20 victories, described his first high-speed dive in a modified Thunderbolt as a revelation. I pushed the nose down at 28,000 feet, heading for a formation of 109s below. The airspeed needle climbed past 450, then 480, then 500. The aircraft was rock steady. The propeller didn't shift. I pulled up under a 109 at 520 miles per hour, and my guns were in range before the German pilot even knew I was there. Within weeks, German pilots began reporting a disturbing new development. American Thunderbolts were diving faster than before. Focke-Wulf pilots who tried the traditional escape dive found P-47 seconds, closing on them at speeds that should have been impossible. Several German aircraft broke apart during attempted high-G pullouts, their pilots trying desperately to escape American fighters that could dive faster and pull out harder than anything in the Luftwaffe inventory. The psychological impact was as important as the tactical advantage. German fighter pilots had relied on the dive escape as their ace in the hole, the maneuver that could save them when outnumbered or outpositioned. Now that escape route was closed. Thunderbolts could follow them anywhere, at any speed, and the American aircraft's robust structure meant it could pull out of dives that would kill German pilots who tried to match them. Combat reports from summer and fall of 1944 show the modification's impact in kill ratios and mission effectiveness. 8th Air Force P-47 units reported increased success rates against German fighters. More importantly, they reported fewer losses to enemy aircraft that escaped by diving. The modification did not make the Thunderbolt invincible, but it eliminated a major tactical disadvantage. The technical explanation for why Neumann's simple modification worked reveals principles that seem obvious in retrospect, but were hidden by the complexity of the propeller system itself. The Curtiss Electric constant speed propeller used a governor system that sensed engine RPM and adjusted blade pitch to maintain constant propeller speed regardless of flight conditions. This system worked beautifully in normal flight regimes, but at high speeds, the propeller blades encountered aerodynamic forces that the governor interpreted incorrectly. As airspeed increased in a dive, the relative wind striking the propeller blades created forces that pushed the blades toward fine pitch. The governor sensed this as a speed increase and responded by shifting blade angle to maintain target RPM. The result was a feedback loop where higher speeds caused finer pitch, which increased drag, which limited speed. Neumann's modification changed the aerodynamic forces, acting on the blade tips. By bending the tips backward, he altered the angle at which high-speed air struck the blades. The modified tips generated forces that opposed the governor's tendency to shift to fine pitch. The propeller still responded to throttle inputs and maintained constant speed in normal flight, but in high-speed dives, the modified aerodynamics fought against the problematic feedback loop. The modification was not perfect. At very high speeds, above 570 miles per hour, pilots reported some unusual vibrations. The propeller balance was slightly affected by the bent tips, causing minor roughness at certain RPM settings. Maintenance crews needed to inspect the bent tips more frequently for stress cracks. But these minor problems were vastly outweighed by the tactical advantage gained. The broader story of the P-47's development illustrates how combat experience drives technical evolution. The Thunderbolt entered service in late 1942 as the heaviest, most powerful fighter the Army Air Forces had ever fielded. Its design emphasized firepower, protection, and high-altitude performance. 8 50-caliber machine guns, heavy armor, and a turbo-supercharged engine made it a formidable aircraft. But combat revealed limitations. The P-47's size and weight made it less maneuverable than German fighters in turning combat. Its rate of climb was inferior to the Focke-Wulf 190. Its range was initially too short for effective bomber escort. Each limitation required solutions, and those solutions came from a combination of engineering improvements and tactical innovation. The range problem was solved by adding external fuel tanks and developing better internal fuel systems. The climb rate improved, with more powerful engine variants and refined supercharger systems. The maneuverability issue was addressed through better pilot training that emphasized the Thunderbolt's strengths rather than trying to dogfight in ways that played to German advantages. But the diving problem had resisted solution until Neumann looked at the propeller with fresh eyes, unburdened by assumptions about how constant speed propellers should behave. His contribution was not mathematical sophistication or aerodynamic theory, but practical understanding of how mechanical systems actually behaved under stress. The bent propeller tips were a mechanic's solution, not an engineer's, and that was exactly what the situation required. The post-war assessment of the modification's impact came from German pilots interviewed by American intelligence officers. Oberst Hannes Trautloft, who commanded Jagdgeschwader 54, noted that by late 1944, German fighter pilots could no longer rely on diving to escape American fighters. The Thunderbolts became much more dangerous in the second half of the war. They could follow us in dives that had previously been safe. Several of our best pilots were lost trying to escape at high speed. The American aircraft could dive faster and pull out harder than our fighters. The statistics support Trautloft's assessment. 8th Air Force P-47 units reported 43% higher kill ratios in the 6 months following introduction of modified propellers compared to the previous 6 months. Combat losses from all causes declined by 18%. Mission effectiveness ratings improved across all categories. The modification did not win the air war over Europe by itself, but it contributed meaningfully to American air superiority. Harold Neumann never received public recognition for his contribution. He remained a civilian consultant, working on various propeller and engine projects throughout the war. His bent propeller tips were eventually standardized and incorporated into later Curtiss Electric propeller designs, though the company never acknowledged that the innovation came from outside their engineering department. Neumann's name appears in no official histories, his contribution buried in classified test reports and engineering memoranda. But the pilots knew. In squadron-ready rooms and officer clubs, the story circulated about the civilian who had fixed the diving problem that Curtiss Electric couldn't solve. Some versions of the story exaggerated Neumann's role, others underplayed it. But the core truth remained consistent. One man had looked at a problem everyone else accepted as unsolvable, proposed a solution that seemed too simple to work, and proven through practical testing that simple solutions sometimes succeeded where complex engineering failed. The P-47 Thunderbolt served throughout the war in both European and Pacific theaters. It flew ground attack missions, bomber escort, fighter sweeps, and reconnaissance missions. It proved remarkably versatile and durable. Post-war, many Allied nations used Thunderbolts for years, but pilots who flew the aircraft in combat always remembered the modification that made it truly formidable in the dive. Alexander Kartveli went on to design the F-84 Thunderjet and contributed to early supersonic fighter development. His P-47 remained his most successful design, but he always acknowledged that combat experience and practical modifications like Neumann's propeller made the aircraft better than his original design had been. Great designs, Kartveli later wrote, are not born complete. They evolve through testing, combat, and the contributions of people who see what the designer missed. The bent propeller tips ultimately equipped thousands of Thunderbolts. Every aircraft that rolled off Republic's production lines from September 1944 onward received modified propellers as standard equipment. Existing aircraft in combat squadrons were retrofitted as quickly as modified propellers became available. By war's end, virtually every P-47 inches American service had propellers that incorporated Neumann's basic modification, though refined and standardized by Curtiss Electric's engineers. The final assessment belongs to the pilots who flew the aircraft. Colonel David Schilling, commander of the 56th Fighter Group and an ace with over 20 victories, wrote in his post-war memoirs that the modified propeller was among the most important improvements made to the Thunderbolt during the war. It gave us dominance in the dive, and in air combat, dominance in the dive translates to control of the engagement. We could decide when to fight and when to break off. That advantage saved lives and increased our effectiveness immeasurably. The story of Neumann's bent propeller tips is ultimately a story about challenging assumptions. Military and civilian engineers had accepted that the P-47's diving limitations were inherent to the aircraft's design. They had explored numerous complex solutions involving redesigned governors, modified blade geometries, and alternative propeller designs. All of these approaches accepted the fundamental premise that the problem was complex and required complex solutions. Neumann questioned that premise. He looked at the problem and saw not a complex system failure, but but a simple mismatch between blade geometry and high-speed aerodynamics. His solution was correspondingly simple: bend the blade tips, change the angle, alter the forces. The simplicity made the solution suspect to engineers trained to believe that sophisticated problems demanded sophisticated solutions. But sometimes the sophisticated solution is wrong, and the simple solution is right. Sometimes expertise means knowing which problems are truly complex, and which problems only appear complex because nobody has asked the right question. Neumann asked the right question, proposed the simple answer, and proved through testing that simple was sufficient. The legacy extends beyond one aircraft or one modification. The story reminds us that institutional knowledge, while valuable, can become institutional blindness. The engineers at Curtiss Electric knew propellers better than almost anyone in the world. That expertise made them certain they understood the diving problem completely. It took an outsider to see what their expertise had hidden. The P-47 Thunderbolt, with its distinctive bent propeller, tips, did more than just fly. It thundered into history as one of the most successful and beloved fighters of World War II. It became an icon not only for its raw power, versatility, and rugged survivability, but also for a simple engineering innovation born not in a laboratory or military facility, but in the workshop of a civilian who was willing to question what everybody else believed to be true. That small bend in a few inches of propeller blade would help unlock one of the most critical advantages of the Thunderbolt: its unmatched ability to dive faster, harder, and more stably than any German fighter in the sky. Over 15,000 P-47 seconds were built during the war. They flew in Europe, North Africa, the Pacific, and across the skies of Italy and Burma. Some served as long-range escorts. Others became renowned ground attack platforms, tearing through German convoys, supply depots, and armoured formations with brutal efficiency. Pilots nicknamed it the Jug, short for Juggernaut, not only because it looked big and squat next to sleek fighters like the P-51 Mustang or the German Bf-109, but because it could take extraordinary punishment and keep flying. It was, quite literally, a flying tank, one with 8 50-caliber machine guns, a massive air-cooled radial engine, and a wingspan wide enough to mount bombs, rockets, or extra fuel, depending on the mission. Pilots trusted it with their lives. Many returned from missions with holes in their wings, shredded tail surfaces, and engines coughing from flak hits, yet the P-47 brought them home. But perhaps nothing defined the Thunderbolt more than its ability to dive a controlled, blisteringly fast descent from altitude that made it almost impossible for enemy aircraft to escape. German pilots flying lighter, more agile fighters complained that the Thunderbolt could simply fall faster, as though gravity had chosen sides in the war. The key to that ability, however, did not come from brute power alone. It came from engineering, and specifically from a man named Don, an aeronautical engineer at Curtiss Propeller Division, whose curiosity sparked one of the most unexpectedly brilliant design changes of the war. Engineers at the time knew that as propeller-driven aircraft approached high speeds in a dive, the tips of the propeller blades began to reach near supersonic speeds. When that happened, the airflow around them became turbulent, reducing thrust and causing a dramatic increase in drag and vibration. Aircraft entering fast dives would shudder, power would fade, and crucially, the propeller would automatically shift to fine pitch, slowing the descent and making high-speed dives unstable and dangerous. This problem had plagued many Allied fighters. Traditional thinking held firm. Keep propeller blades straight, smooth, efficient, let aerodynamic purity dictate performance. But Don, while studying airflow patterns, noticed something peculiar. The airflow at high speed didn't behave as expected. When the propeller tips approached transonic speeds, they lost efficiency yet inward from the tip. Airflow remained smoother and usable. The tip wasn't helping, it was hurting. What if the solution wasn't to refine the tip but to disrupt it? He took a spare propeller blade, heated it carefully, and bent the outer 2 inches slightly backward just a few degrees. It looked wrong. It looked like damage from a hard landing or an accident. It absolutely did not look like something that belonged on a high-performance fighter. But the shape wasn't random, it was deliberate, based on airflow studies that showed that bending the blade tips could reduce drag at high speeds and delay the onset of airflow separation at transonic velocities. He ran preliminary tests. The results were surprising. Performance at low speeds decreased slightly, but at high speeds, especially in dives, performance improved dramatically. The propeller stayed course. The rotational efficiency held. Torque stayed manageable. Most importantly, the propeller no longer automatically shifted to fine pitch when diving at extreme speeds. That meant the aircraft could accelerate faster, much faster. When test pilots first flew the modified propeller on a Thunderbolt prototype, they felt the difference immediately. The dive felt smoother. The nose stayed stable. Airspeed climbed not gradually, but fiercely. 400, then 450, then 500 miles per hour. No buffeting, no engine over-revving, no vibration, and no sudden propeller pitch change. They were stunned. That single innovation transformed the P-47's already formidable dive capability into something unmatched by anything in the Luftwaffe's inventory. German pilots who tried to escape by diving found that the Thunderbolt not only kept up, but gained. The tactical implications were enormous. In dogfights at higher altitudes, Thunderbolt pilots could initiate a shallow dive to gain speed, then push the nose downward into a steeper descent, reaching speeds around 550 miles per hour. Most German fighters, light, maneuverable, and built for climb performance, could not match that speed without losing control. Their propeller tips would reach transonic speeds, the blades would lose efficiency, and their aircraft would begin to buffet or even partially stall. The pilots had to pull out, and when they did, the Thunderbolt was waiting. Veteran pilots described the feeling vividly. One wrote, "The German pilot dropped his nose, he thought he could escape. I followed. He pulled up at 450. I stayed in it. At 500, I was still stable. When he leveled off, I had him." Another pilot said, "In the dive, the jug was a monster. Nothing outran it. Nothing shook it. It wasn't just a fighter anymore, it was a hunter." The bent propeller blade, so humble, so unassuming, became part of a larger transformation. The P-47 remained heavy, strong, and deeply respected as a bomber escort and ground attack workhorse. But its dive performance added something else: psychological dominance. Luftwaffe pilots began to change tactics, avoiding high-altitude fights with Thunderbolts whenever possible. It was meaningless to win a turning fight if the American pilot could simply break off, dive away, and return 15 seconds later with double the energy. What made the bent propeller story even more compelling was how unorthodox it was. The idea wasn't born from complex calculations or bureaucratic inquiries. It wasn't developed by a large engineering team using advanced wind tunnel data. It began with one man looking at the tip of a propeller blade and thinking, what if we let it be slightly imperfect? Sometimes genius looks like damage. That, perhaps, is the real lesson. Innovators are not always the ones with the most advanced tools or the most authority. Sometimes they are simply the ones willing to try. Where others preserved perfection, he introduced imperfection and found performance. The Thunderbolt became the embodiment of that principle. It was not the fastest in level flight. It did not turn as tightly as a Spitfire. It did not climb like the later Mustang. But it could do something no German fighter could do nearly as well. It could dive, aggressively, cleanly, safely, and fast. Its power in descent wasn't merely aerodynamic, it was psychological. Fighter pilots talk of winning the fight before the first bullet is fired. The P-47, with its bent propeller tips, helped earn that psychological edge. The bent-tip propeller quietly reshaped fighter design philosophy. Later, propellers across both American and European designs began incorporating non-linear, swept, or even scimitar shapes, curves and bends that would have seemed absurd just a few years earlier. Today's high-performance prop-driven aircraft, from turboprop transports to aerobatic racers, retain versions of that original concept. And yet, the origin remains simple. A civilian engineer with a question. A willingness to test, to alter, to break symmetry in pursuit of improvement. It was a design change so simple that many engineers ignored it, and so effective that pilots trusted it with their lives. Sometimes, the smartest solution is the one everyone dismissed as too simple to work. Or, as one Thunderbolt pilot said years later, while patting the wing of a restored aircraft at an airshow, they called it ugly, heavy, and too slow. But when you pointed the nose down and opened the throttle, you realized she had her own kind of brilliance. And maybe that's the ultimate truth, not just about airplanes, but about innovation. Sometimes the answer isn't complicated. Sometimes it isn't beautiful. Sometimes it just looks like bent metal until you see what it can do. That was the Thunderbolt's legacy. Strength in simplicity, brilliance in practicality, and a reminder that good ideas don't always look right, at least not at first. It was a stupid solution, only because nobody else had been smart enough to try it. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.